So it's my great pleasure to introduce Avi Pfeffer, who's an associate professor at Harvard. He graduated from Stanford in 2000 with his PhD thesis in models of probabilistic reasoning. He, although he did a stint in database work a long time ago, what he does now is basically modeling, and especially graphical modeling, with a variety of applications. In fact, the reason he's here right now is at the International Symposium on Music Information Retrieval.
That's it.
Yeah, okay. Which is being held at Hopkins and the Library of Congress, because he's been working on modeling music lately. But what we asked him to talk to us about today is a language that he's built for basically for building graphical models. So and doing inference on them. So if you know about Jeff Billman's work at the last couple of summer workshops here, this is sort of, in a sense, that to the next level, because it's not limited to the particular kinds of models that Jeff's looking at. So rather than trying to get this talk for him, being able to
Thank you.
turn the floor over.
Okay, so today's talk is all about reasoning under uncertainty. When we're trying to do AI, we have to deal with uncertainty. Uncertainty is ubiquitous. Any agent that we try to build will only have limited amounts of information about the world. And that partial information that it does have will tend to be noisy because its sensors are noisy. The agent can take actions, but its effects are non-deterministic. And the agent has to reason about various events that are completely outside its control, exogenous events. So for all these reasons, reasoning under uncertainty is one of the central challenges for artificial intelligence. Now, my approach and that of a large part of the AI community to reasoning under uncertainty is to use probability theory. Probability provides us with a sound mathematical basis for dealing with issues to do with uncertainty. And one of the really nice things about probability theory is that when you put it together with utility theory, you get a way to make decisions using the maximum expected utility principle. So in principle, probability is really nice. But in order to make probabilistic reasoning work, we need a number of things. We need, first of all, a representation. We need a way to describe probabilistic models of the world. And these representations should be compact, they should be natural, easy to understand, various properties that we would like from the representation. We also need inference algorithms. Given a particular representation of a probabilistic model, we need to be able to ask queries about that model. A typical kind of query would be to say, given that we've observed a certain set of observations, a certain set of evidence, what is the probability of some entity of interest that we're interested in? And that's just a conditional probability query. And finally, we need algorithms for learning our probabilistic models from training data. So those are the things we need to do. The challenge is, how do we do them when we're dealing with real, interesting, large, complex domains? So we want to construct probabilistic models of large, complex domains. They should be easy to construct and understand. They should support efficient inference. They should be learnable from data. Now, this is analogous, but somewhat slightly different from the programming challenge, which is, again, if we're interested in large, complex problems, how do we build programs for interesting problems that, again, they should be easy to construct and maintain. They should do the right thing. They should run efficiently. So there are lots of answers to this question in the probabilistic domain, lots of different kinds of models that people have dealt with. Bayesian networks, hidden Markov models, stochastic context-free grammars. Those are three that I'll talk about during the talk. A lot of new models are being proposed all the time. A couple of languages that I've worked on. One is object-oriented Bayesian networks, which is like Bayesian networks, except that variables are associated with objects, and you talk about the way objects interact with each other. Probabilistic relational models, which I'll also talk about later in this talk. So, given that there are all these representations, I said to myself, wouldn't it be nice if instead of having to come up with a new representation language all the time, every time you wanted to do something new, if there was a single representation language that will allow you to express all these different kinds of models. So we want a general purpose probabilistic representation language that captures many existing kinds of models of different flavors. Also, it will naturally allow many new models. And in addition, when I thought about this, I was thinking about the analogy between the probabilistic reasoning challenge and the programming challenge, and the fact that we have lots of tools in programming languages for constructing large programs and maintaining them. So we should use some of the ideas from programming languages for building and maintaining our models. So this talk is about such a language. It's called IBAL. It stands for Integrated Bayesian Agent Language, but you should forget that. IBAL is a high-level, I call it, probabilistic programming language. It can represent a wide variety of probabilistic models. In addition, it can also represent decision problems where an agent has some choices and has a utility associated with various outcomes. It also supports parameter estimation in a Bayesian paradigm. And I've implemented this language, and it is publicly available. I'll give you a URL at the end of the talk. So I'm going to talk about the language itself. I'll give you some examples of types of models that you can express in the language. And then I'll turn to the subject of inference. I'll talk about the general goals of inference. And the goals are motivated by all the different types of things you can express in the language. And then I'll talk about how I actually implemented the inference so as to achieve those goals. So the basic idea behind IBAL is the idea of a stochastic experiment. An expression in an ordinary programming language is basically a process that generates a value. You can think of it as an experiment that produces some value as the output. An expression in IBAL is similar, except that it doesn't just generate a single value, it stochastically generates a value. So it corresponds to the notion of a stochastic experiment. Now, it's important to note, though, that the meaning of an IBAL expression is not the stochastically generated value. It's the probability distribution over the value that would be generated by this stochastic experiment. And evaluating an expression does not mean just sampling the process to get a particular value. It means computing the entire probability distribution over the outcome. So let's have a look at some simple expressions. You can have a constant be an expression, so I can define the variable x to always take on the value below. So a constant means now with probability 1, it takes on the value below. Variable assignment, conditionals, just as in an ordinary programming language. The new construct here is the dist expression. So here I say that W is dist, then 0.4 hello, 0.6 world. Dist means a stochastic branch on two different possibilities, where with probability 0.4 we take the first branch, with probability 0.6 we take the second branch. So in this case, I'm saying that W is with probability 0.4 equal to hello, but with probability 0.6 world. Of course, like any programming language, we can have functions. So here, I've defined a fair function which takes 0 arguments, and it corresponds to the act of tossing a fair coin. So when you invoke the fair function, you get as a result with probability half heads and with probability half tails. And then I can define two different invocations of the fair function, x and y.
Which are now IID random variables, is that right?
Okay. Exactly. Yes. So x and y are going to be independent tosses of this fair coin. IBAL is actually modeled after functional programming languages. So you can have higher order functions in IBAL. Functions are first-class objects. Here's an example. So the first row is the fair function that we saw before. The second row is very similar. It's the biased function, which corresponds to tossing a coin that's biased towards being heads. The third line is a higher order function. It corresponds to the act of picking either a fair or a biased coin. But the fair or biased coin itself is a function. It's something that can be tossed repeatedly. So with probability half, we return the function fair. With probability of half, we return the function biased. Then I can define a particular coin to be an invocation of this pick function. So the result of picking either the fair or the biased coin. And then I can define, so coin is a variable whose value is functional. And then I can define two invocations of the coin, whatever the coin happens to be. So, are x and y independent of each other in this example? Well, the answer is that they're not independent of each other because they depend on the value of coin. They are conditionally independent given coin. So if I know what the coin is, then they're two independent tosses of the coin. If I don't know what the coin is, however, suppose I tell you that x came out heads. Well, x is more likely to come out heads if it's a biased coin than a fair coin. So that provides a little bit of evidence that it might have been a biased coin. So since there's some evidence that it might have been a biased coin, that's a little bit of evidence that y might have come out heads. So when x comes out heads, that increases the probability that y comes out heads. They're not independent of each other, but they are conditionally independent of a given coin.
So let me make sure I understand. So when you first put up pick as a distribution 0.5 fair, 0.5 bias, my first intuition was to think of pick as another random variable which has a mixture distribution. But you're saying that's not its semantic.
That's not, because I have these parentheses here, that's indicating that pick is a function. So pick, the pick is deterministically the function that when it's instantiated returns either a fair or biased coin.
The function fair or the function bias.
Right.
And the function fair and the function bias are random variables. Okay. So
Right.
now, okay.
So
Go ahead.
So the two primes are sort of like a sampling operator?
Yes, you can essentially think of an expression as being a sampling operator. When I say a stochastic experiment, that's something that you can sample. Except that the meaning of it is not the sampled result of the actual distribution.
The two parentheses are taking sample.
The parentheses are applying the function to zero arguments in this case, because it's a zero argument function.
So to be clear, x and y are not pure heads and tails. They're still random variables.
X and y are random variables, right? Yes?
So the definition of the pick function, fair, if that had parentheses after it, it would be evaluated and fixed to a particular heads or tail value, but since there's a parentheses, the function is the value, so it's evaluated every time we call pick. Is that right?
If there were parentheses where? Over
After
here?
fair, the definition of pick. So it's
Yes,
the
right.
function or the evaluation?
Right. If there were parentheses after the definition of fair and after the definition of biased, then you would actually, as soon as you picked the coin, you would also toss it. So it would correspond to the act of picking and tossing a coin.
So if you without the parentheses, it's like a random variable. With parentheses, it's the value of the variable. Is that right?
With parentheses, it's just a different random variable, which without parentheses, it's the function object. With parentheses, it's what happens when you execute the function. Okay?
So if it's on the right-hand side, so on the left-hand side, you're generating it.
If it's on the left-hand side here, that's the syntax for defining a function. Yes.
So coin selects pick, which selects either fair or biased. Is this correct?
Right.
And and it selects it. So if X then becomes biased,
No, X can only be heads or tails.
I know, but it's picked by bias.
Correct. If it's picked by bias, yes.
Then Y is picked by bias as well.
Correct.
In other
Yes.
words, whatever coin comes out in the first instance, there's not a separate experiment.
Right. That's correct. Yes.
And is that clear from the notation?
Yes. Coin is a random variable whose value is the result of applying pick. So that means the value of coin has to be either fair or biased.
Right.
If the value of coin came out to be biased, then that means that its value in all future invocations is biased.
And when can I do it again?
You can define another coin
So that
to
would
be,
be then coin 2.
that would be coin 2, yeah. Yeah, you can't redefine variables. It's a functional programming style, so variables are defined once.
So you can't have another line that says coin equals pick this time.
Right.
Again.
Right.
Sorry, excuse me, the definition of pick, if we had fair with parentheses and bias with parentheses, then we would have independent X and Y every time we invoke the coin.
If you had fair with parentheses and bias with parentheses, it wouldn't make sense to do coin equals the result of picking, because the result of picking would be heads or tails now.
Yes. And then coin would be
And
at a very
so you would go X equals pick, Y equals pick, and yes, indeed, they would be independent in that case.
Okay.
Okay, so I should add that I've just shown you the basics of the language. There are also lots of features in the language for defining data structures. It's a strongly typed language with automatic type inference. And now let me talk about some examples that can be expressed in IBAL, some well-known and then not so well-known models. So, okay, who in this room is familiar with Bayesian networks?
AKA graphical models.
Okay, pretty much everyone. So I don't really need to explain very much. Just to say that we have a graph. It has nodes corresponding to each of the variables we're interested in. This example talks about a student who's taking a course. So whether or not the student is smart, whether or not the student is diligent, good test taker, understands the material, the exam grade that the student gets, and the homework grade. And an edge encodes direct influence from one variable to another. So for example, the grade that someone gets on a homework depends directly on whether or not they understand the material. And this is the qualitative structure of the model, and it encodes a lot of conditional independence information. For example, it encodes the information that homework grade is conditionally independent of smart given understands material. But in addition to this qualitative information, there's also quantitative information where with every node we have a conditional probability table that gives us the conditional probability of that node given its parents. So here, for example, we have the conditional probability of understands given its parents smart and diligent. And that tells us for every combination of values of the parents, the probability of the node. So for example, it tells us that if the student is smart and diligent, then the probability they understand the material is 0.9. If the student is smart and not diligent, the probability is only 0.3, and so on. So that's a Bayes net. It's the qualitative information and the quantitative information. Between them, they define a complete joint probability distribution over the domain. So it's quite simple to represent a Bayes net in IBAL. We have a definition for each of the variables that we're interested in. We start with the roots of the network, so we go in topological order. So we start with the root smart and flip 0.8, that's just a shorthand that I use to say it's the same as dist 0.8 true, 0.2 false. It just means with probability 0.8 it comes out true, and with probability 0.2 it comes out false. Similarly, diligent with probability 0.4 is true. Now for a variable that has parents, we look at the values of the parents, and IBAL has a case expression to case over the possible values of the parents. So for the understands variable, we case over the values of smart and diligent. And then we say, if smart is true and diligent is true, then understands is true with probability 0.9. If smart is true, diligent is false, understands is true with probability 0.6, and so on. Another model that you're probably all familiar with is hidden Markov models. So in a hidden Markov model, we have some hidden state that develops according to a Markov process, and then at each point in time, we have an observation that depends only on that hidden state. And to specify an HMM, you need to specify three models: the initial distribution over the initial hidden state, the transition model of one hidden state given the previous hidden state, and the observation model, which gives you the probability of an observation given the hidden state. So all this is very, very standard, but in ordinary HMMs, the state is something atomic. It's one out of a certain set of states, and it has no internal structure to it. In IBAL, one can easily imagine having the state being a member of some data type that has some internal structure. It might even be a first-order data type. So the hidden state could be a tree. And now the transition model would take a tree and produce another tree. And so you get a notion of first-order HMMs. So how do you specify HMMs in IBAL? It's quite simple. For the initial model, transition model, and observation models, I've just defined their types. So these are type statements. The initial model is a function that takes 0 arguments and produces a state as a result. The transition model takes a state and produces another state. The observation model takes a state and produces an observation. So whenever you have a model that expresses a conditional probability, like the probability of an observation given a state, the way to think of that in IBAL is a function from the state to observations. And then we just define a sequence function that corresponds to executing an HMM from a particular current state. So we set the first state to be the current state. We get an observation from the observation model. And then we get the future by applying the sequence function to the result of applying the transition function to the current state. So in other words, we take the current state, pass it through the transition function, that gets us a new state, and the future is a sequence beginning with that new state. And the HMM as a whole is just a sequence beginning with the result of applying the initial model.
Just go back, please. What does observation equal state into observation? So what's
the three lines up.
no, you understand.
This one?
Yes, that's right.
That's a type declaration. I'm saying that obs, this notation is functional programming notation for a function. It's a function that takes a state and returns an observation. So the observation model, I guess.
So the two obs on the left and right are different obs?
Yes, I should fix that. They should be different. I'm sorry.
So the obs on that line
This is
the
the
right
function.
hand ob.
It's the
So
left
the left hand
ob.
ob.
Yes.
Yeah, okay, because it's a function. All right.
So you could have, in the previous example where you had smart, diligent, homework and stuff like that, you could have written that using these as well. You could have defined an operation that says test taking is given by, is a function that goes from smart to...
Yeah, I could have, well, not exactly. These definitions are on types, not on variables. There's no such variable as state.
Because you had a case condition for...
Right.
So that
Right.
could be implemented. Could that have been implemented?
It's a little bit different.
Okay.
The variables smart and diligent have types.
Okay.
And
Booleans.
Booleans in this case. Yes, they're Booleans. And similarly, understands material is a Boolean. And so if you wanted to write a function for understands material and gives it a type, its type would be Boolean times Boolean to Boolean. It would take two Booleans and return a Boolean. That's how it works. Another very familiar framework is stochastic context-free grammars. So here we have non-terminal symbols like S, A, and B, and then we have terminal symbols like small a, small b. And associated with each non-terminal symbol, we have a set of productions, and we have a probability distribution over the productions of each non-terminal symbol. And so you can imagine a simple way to think of a non-terminal symbol in a stochastic context-free grammar is as a data-generating process. When you get the symbol S, you can apply it as a function, and eventually you'll end up with some data at the bottom. So let me show you what this looks like. First, so in order to define stochastic context-free grammars, we need to be able to work with strings. We need an append function. This is just the standard way of writing an append function. Then I define what it means to have a production of two different non-terminal symbols. And that's just the result. So if I have two non-terminal symbols and I have a production with them, the result of executing this production is the same as taking the result of executing the first. So I have parentheses after this x, the result of executing the second, and then just appending them together. So that's what a production is. Terminal is very simply, the terminal with a particular terminal symbol is just a singleton list of that terminal symbol. Once I've set up this infrastructure, then I can write down stochastic context-free grammar almost exactly as it's written on paper. So S, the non-terminal symbol S is now a function that when you execute it, you get with probability 0.6 the production of A and B, with probability 0.4 the production of B and A, and so on. So it becomes very simple. Okay, now for a language that's probably a little less familiar to you, which is probabilistic relational models, which I worked on with some colleagues a few years ago. And the idea is this. We have a relational database with several relations. In this case, we've got an actor, a movie, and an appearance relation. And in each relation, there are some attributes. Now, some of those attributes are keys to either that relation or to the other relation. So the actor relation has a key, which has an actor key. The appearance relation has a foreign key, which is the actor, which is a key to the actor relation. But then there are some other attributes, which are what we call value attributes, which you might have uncertainty over. So they may not always appear in your database. So we want a probabilistic model over the values of these attributes in the database. And the way we set it up is with statements that relate one attribute to other attributes, which could be attributes of the same relation or of other relations. So in our example, we say that the role type of an appearance depends on the gender of the actor making the appearance and the genre of the movie in which that appearance is made. And this is a general rule that you only have to state once, and it applies to all instances. In particular, it tells us that the role type of Charlie Chaplin in Modern Times depends on Charlie Chaplin's gender and the genre of Modern Times. associated with this rule also is a conditional probability table that quantifies the uncertainty that we have. So here's a schematic description of how you would describe a PRM, a probabilistic relational model in IBAL. So we've got a function for every relation in the database. There's a function for the movie relation, and that defines the genre attribute to be some distribution. Another function for the actor relation defines the gender attribute to be some distribution. Now the appearance relation has as foreign keys an actor and a movie, so it takes as arguments an actor and a movie. And now the role type of the appearance can look at the gender of its actor argument and the genre of its movie argument. And then it cases on those things, and then you get distribution over role type accordingly. That's the definition of the model schema, but in order to actually make it useful, you have to define some instances. So that's what happens here. We say, okay, modern times is an instance of movie. Well, you just get that by applying the movie function. Charlie Chaplin is an instance of actor, and there's an appearance which we'll call A1, which is the result of applying the appearance function to the arguments Chaplin and modern times. And so that builds the instances and connects them together, and their probabilistic model will be defined by these relationships here. Okay, one thing I haven't mentioned, but is very important, is asserting observations, conditioning the domain. So whenever you have a probabilistic model, you want to say, well, not only do I have this model, but actually I observed that this particular student got a very good homework grade. So you want to be able to assert observations. You can do that anywhere within an IBAL program. All the examples I've showed you, the probabilities have been actual numbers, but in fact they can also be parameters, learnable parameters, and you can supply Bayesian priors for them. You can also talk about decision problems where an agent has a decision variable, decisions to make, and utilities associated with different outcomes, and this allows you to encode frameworks like influence diagrams and Markov decision processes. Okay. So that's the language. Let's talk about inference. How do we do inference in this language? So first of all, some high-level goals. So the language generalizes many frameworks in its representation. You can represent Bayes nets, hidden Markov models, stochastic context-free grammars in IBAL. It should be the case that the inference algorithm for IBAL is able to simulate inference algorithms for these different frameworks. If it doesn't, if inference in IBAL is hopelessly inefficient for these frameworks, then what use is it that you can actually represent them in IBAL? So we have to have an algorithm that generalizes many standard inference algorithms. We need to support parameter estimation for learning the probabilistic parameters and support decision making for the decision problems. In the probabilistic reasoning component, which is what I'm going to focus on, there are a couple of things we need to do. One is we have a language which allows highly structured models to be expressed. And we really need to take advantage of language structure, and I'll show you what that means in a moment. And another goal is to avoid unnecessary computation whenever we can. So all these considerations led to a series of desiderata for the inference algorithm. The first one is basic for any probabilistic representation language that is trying to express graphical models, which is you have to exploit independence. Bayesian networks exploit independence. That's what they're good at doing. So we need some sort of Bayesian-like inference algorithm to exploit independence. In addition to independence, though, there's actually more structure that we can try to exploit, which is low-level structure within the conditional probability tables themselves. One kind of structure is what's called the noisy OR structure. And here the idea is that Z depends on x and y. And z is essentially the OR of x and y. It's basically x or y, except that there's a noise factor associated with each side of the OR. And that's called the noisy OR model. We want to be able to exploit those kinds of compact models. Another kind of low-level structure we want to exploit is what's called context-specific independence. This is a situation where one variable is conditionally independent of another only under certain circumstances, only under certain values of a third variable. Here, z depends on x and y. When x is false, we look at y to see whether it's false or true. When x is true, however, we don't bother to look at y. So we have a situation where z is independent of y in the context that x is true. And we want to be able to exploit that kind of structure where we find it.
So if I understand the last two slides right, these are both cases where you have fewer than 4 parameters in the dependence of the disease on the symptom on the disease that it's with.
Yes, exactly.
And you want to exploit the fact that you have fewer than 4 parameters. You've got a sparse model, so you want a sparse computation.
Yes, exactly. Another kind of structure that you want to exploit is more of a high-level structure that holds between objects and the domain. So one thing that was important in the development of object-oriented Bayesian networks was the intuition that a complex domain often consists of weakly interacting objects. And these objects only interact weakly. They only share a small interface with each other. For example, if we have two different students who are taking the same course, then the only variable that the students share is the difficulty of the course. And except other than that variable, or the students are conditionally independent of each other, given that variable. So when we have object structure, we want to try and exploit the conditional independence that goes along with it. Now for avoiding unnecessary computation. Well, one obvious case is where we have the same function repeated over and over again. Like here we have some complex function f that's repeated 100 times. We want to avoid doing the inference for it 100 times. It seems like we want some sort of memoization capability here. Another notion of avoiding the computation is using the query and only performing those computations that are actually necessary for evaluating the query. And sometimes that can save a lot of computation. Sometimes that can turn an infinite computation into a finite one. Here's an example. We have a divergent function f, and then x, it looks like it depends on f, except that the value of x is always true. And so in order to know what the value of x is, you don't actually need to look at f. So if you use the query, you can avoid doing this infinite divergent computation. And lazy evaluation is precisely the mechanism that gets us this property of avoiding, of using the query and only doing the computation for a query. And in programming languages, lazy evaluation is somewhat controversial. It has its advantages, but it also has a lot of disadvantages in that it's quite hard to understand programs that are written using lazy evaluation. At least that's a claim that's often made. But I would argue that for a probabilistic language, it's absolutely necessary, because it's basic to the way we build probabilistic models. When we define a stochastic context-free grammar, we might define a grammar that can generate infinitely, or not infinitely, but arbitrarily long sentences. And then we ask the query on that grammar, what's the probability that it generated a particular sentence of some finite length? Now, without lazy evaluation, you would have to go and look at all the arbitrarily long sentences that the grammar could generate. It's only lazy evaluation that allows us to perform the computation in a finite amount of time. So implicit in the algorithms for stochastic context-free grammars is the notion of lazy evaluation. So for that reason, I believe that it was absolutely necessary.
Don't you need it just for your HMM example, since you defined the HMM when samples were returned infinite? Oh,
Yes, because I have lazy evaluation, I felt free to define the HMM example that way. Yes. Right. A related but somewhat different idea is, rather than using the query to limit the amount of computation that gets performed. We use what I call the support of variables. In probabilistic reasoning, the support of a variable is the set of values that that variable can take on with positive probability. And if you can do a certain amount of reasoning to figure out that set of values, you might be able to simplify the computation. Here's a very simple example. Again, we have the divergent function f. We have a variable x, which is defined to be false, and then y looks at x, and if x is true, evaluates f, otherwise just returns true. Well, because x is known to be false, we know that we don't have to look at the true clause of this if expression, and we can avoid this divergent computation. Now, this is a very simple example of using support. Sometimes you actually have to do a certain amount of computation to calculate the support, but it's still a useful thing to do. And a third variation on this theme of using whatever information you can to avoid computation is using evidence that you might have. So evidence is a little bit different from support. Here we have the same example as before, but here x could be either true or false. With probability 0.6 it's true, with probability 0.4 false. So if we just look at the support of x, we wouldn't have to look at the divergent computation. But we also have an observation about x, that x actually came out to be false. And we can use that observation to infer that we don't have to look at the divergent computation. So those are three different sources of information: the query, the support, and the evidence that we can use to limit the computation. Okay, so those are the basic goals that I had in designing the inference algorithm. Here's how the algorithm works. So it's basically a two-step algorithm. In the first step, we decide what computations need to be performed. In the second step, we actually go ahead and perform the computations themselves. And I should tell you, it was actually quite a breakthrough when I realized that we needed this two-phase framework. Because at the beginning, I tried to do everything in one phase. So this division into two phases, it provides us with a nice division of labor and a nice way to organize how we deal with the different desiderata that I talked about. So phase one is basically the phase that's responsible for avoiding unnecessary computation, because this is where we figure out what computation needs to be done. So this is where we look at the query, we look at the support, we look at the evidence. This is also where we take advantage of repetition and avoid repeating computation. Phase two, where we actually do the computation, is where we have to take advantage of the structure. Whether it's ordinary conditional independent structure, or low-level structure, or the higher-level structure that holds between objects. So let's start with phase one. So phase one takes an IBAL program and produces a data structure that I call the computation graph. In this computation graph, there's a node for every sub-expression in the program. And there's an edge from a node x to node y if y needs to be computed, if sub-expression y needs to be computed in order to compute expression x. So it sounds like an evaluation tree, except it's a graph, it's not a tree, because we ensure that no sub-expression appears more than once in this graph. So different expressions can share the same sub-expression. And we're going to use memorization, which is a standard technique of recording each time you see something and making sure that you never, if you've seen something before, you never redo the work for it. We use that to make sure each sub-expression occurs once in the graph. So constructing the graph, constructing the computation graph, there are two things basically that happen. The first is that we look at the evidence that we have about variables, and we propagate the evidence throughout the program as much as we can. And then we compute the support for each node. So here we're looking at the evidence, we're looking at the support. Those are two of the things that I wanted to do. Looking at the evidence, that is a process that it's very complicated. It goes in both directions. So you can have evidence about the variable, and that can propagate backwards to where the variable was defined. It can also propagate forwards to other uses of the variable. So for example, here, we have an observation that the A component of the variable x is true. Well, that is propagated backwards to the definition of x, and it can be propagated inside here to the A component. We know that this particular flip came out to be true. It could have been true, it could have been false. It came out to be true because of our observation.
Excuse me, I don't understand. Is there some order in it? So, after carrying out, so this is a definition. Is this a program or?
This is a little program, yes.
So I first let x equal this thing.
Right.
And only then I observe.
And only then you observe that it's... So you say x is a
So I
toss-up
don't in fact
point.
compute it.
And
I don't in fact compute the x. I keep going and only later on do I go back. Is this true or am I?
Yes.
Huh?
Yes. You,
Yeah.
you don't have to find the whole distribution at the time you define x.
yes.
You find only the parts that you need after you absorb things and make queries. Yes?
Yes.
And how deep do I go before I finally?
Well, it
Or
depends.
do I not understand?
If you need, in this program, we actually need to know what the A component of x is.
Yeah.
So once we've got the observation, we propagate that observation backwards, and we now know that the A component of x is actually true. Because we get this out of the definition of x. So we have to propagate the observation backwards into the definition of x so we know it's true. And then we propagate that forwards to the appearance of x dot A, and now we know that in the appearance it had to be true. So that's...
Well, I have difficulty with it. Okay.
Alright.
So I guess the question you had was how far do you need to look?
That's
I think the
yes.
answer is you have to look at the entire program.
So actually, the answer is a little more complex. This observation propagation is only an optimization, actually. It's only being done to try to avoid unnecessary computation. I could not do this phase, and later on I would take into account the observations in a completely different way and essentially multiply them together with the other definitions. And as I multiply everything together, I will get all the observations in there and get the right answers out. And at that phase, you go as far down as you need to go. In this phase of propagating the evidence, because it's only an optimization, it's only shallow.
Maybe, what does the in mean there?
Oh, that's just...
Is this a concatenation or something?
It's just a sort of a sequence. It's not a sequencing. It's a way of constructing expressions. It's standard functional programming notation to say let x be this in the x. So I'm defining the variable x to be something in another expression, and I'm observing x dot a to be true in this other expression.
So it's a local scope for a value assignment.
It's
The scope of that value assignment is
yes.
follows.
Yes.
Can I ask you a question?
Yeah.
So when you're doing the construction and the computation graphic optimization, would it be true that there are some things you can't? How do you tell what you can't evaluate at compile time? So you're doing this at compile time, is that right?
There is no compile time.
There's no, so it's all.
It's all basically runtime.
So you use optimization on the fly, the whole.
So yes,
Okay.
yes. Okay, so that's the first step, propagating evidence. The second step is we compute the support for each node. in our computation graph. And what does the support mean? It means all the values that the variable can actually take with positive probability. Well, if you think about it, that's the same as saying, what is the set of values that a variable can take in a non-deterministic programming language? So computing the support is essentially the same as writing an evaluator for a non-deterministic programming language, which is a well-understood problem. And with the caveat that we want to do it with lazy evaluation, for the reasons that I mentioned earlier, and also we want the memoization to avoid repeating computation. We want to be able to reuse results whenever possible. So it turns out that that doesn't work. You can't do lazy evaluation and memoization together, or at least not in a simple way. Why not? Well, how does memoization work? Memoization says whenever you call a function, whenever you apply a function, you look up the arguments in a cache. If you see them, you reuse the result. If you don't see them, then you go ahead and evaluate the function. With lazy evaluation, you don't have any arguments to look up in the cache at the time you call the function. The arguments are not evaluated at the time that the function is called. So what can you possibly do? So when I spoke to programming language people about this, they told me, oh, it's hopeless, I should forget the idea. But I decided to persevere, and I came up with a version of lazy memoization. And the idea is this. We're going to, whenever we apply a function, we're going to start out, we're not going to evaluate any arguments, because we want to be lazy. And we're going to try to evaluate the function without any arguments evaluated. So that's probably going to fail. At some point, we're going to find out that an argument is needed. Well, at that point, we abort our speculative evaluation of the function. This is an important step. We're going to store in the cache the fact that the argument is needed. So we're not storing any result in the cache. We're just storing the argument that's needed in the cache. Okay. Once we've done that, we then go ahead and evaluate the argument, and then we try again to evaluate the function, this time with this one argument bound, but with other arguments still unevaluated. And we continue this process until finally the function evaluation succeeds. When it eventually does evaluate successfully, then we catch finally the mapping from the arguments that we've already evaluated to the result of the function. Let me give you an example. So here, we have a function f that takes 3 arguments x, y, z, and it's just defined to be if x, then y, else z. And we're going to apply f to the arguments true, a, and b. So what happens in this case? Well, we're applying f. The first time we apply f, we try to apply it with no arguments bound. So we try to apply f with no arguments bound, and then the first thing we see is if x. And that tells us, wait a minute, we can't succeed in evaluating the function because we need x. So we abort the function evaluation, and we store in the cache the fact that if you try to apply f with 0 arguments, you're going to get the result need x. You're going to get the fact that you need x. By doing this, you'll prevent yourself from ever again trying to apply f with no arguments. You'll always, from now on, evaluate x before applying f. Okay, so then we go and evaluate x, which is true in this case, and we try to apply f with only x bound to true, and we see, okay, if true, then we look at the true case, we need y. So we again abort the computation, and we store the result that if we apply f when x equals true and nothing else is bound, then we will need y. Finally, we evaluate y, we apply f with true and a bound, and in this case, we don't need z because z is in the else clause, which we don't need to look at, so the function evaluation can succeed. And we store this mapping from these arguments to this result in the cache.
So what would happen is, just to understand this example, if memoization was not there, but still things were lazy, this example, what would be different?
If memoization was not there, what would happen is you would try to evaluate f with 0 arguments bound, when you got to x, you would go immediately evaluate x and then continue in the evaluation of the function f, and then get to y. You wouldn't have to abort. So there is a cost that you're having to abort the computation in order to get the memorization.
So you're memorizing based on the actual value. So if I then did f of false of c and d, I'd have to go through this process again because
right. You save the first step.
match f of true.
Yeah, you'd save the first step because you know right away you have to evaluate x. But then for the second step, you need to go and do it if you get need z. Okay? So that's it for phase 1. So just to summarize, we propagated the evidence, then we constructed, we computed the support for all the nodes, and that was basically an evaluator for a non-deterministic programming language, but it was using the lazy memorization trick. Phase 2, so we start out with this computation graph, and we turn each node into a data structure that I call microfactors. And from that data structure, we can compute the solution. So microfactors are very simple. They're just a representation of a function from the values of variables to reals, but it's not quite a table. You notice that in this microfactor, we have a row that says x is true and y is don't care. So you can think of it as a table with don't care, or where in some entries variables can take on multiple values. The reason I use this data structure is because it allows me to represent that type of context-specific independent structure, that low-level structure that I talked to you about earlier. So what are these microfactors that we're trying to produce? The essential idea is we take an IBAL program and we want to translate it into a set of microfactors and also a set of temporary variables such that the answer that we want to compute, the probability of the output, is the product over all the microfactors in my set, and then I take the sum over those temporary variables. So I want to get this sum of products expression. Why do I want to do that? Because it's very similar to the way inference in Bayesian networks is stated. It's also stated as a sum of products expression. And when you have a sum of products expression, you can use an algorithm called variable elimination that exploits independence in order to solve it. So to produce these microfactors, we just work with the computation graph. We work on every node. We use rules that tell us how to translate each particular node. We have ways, these rules might tell you to introduce temporary variables. That's a technique that we can use. Let me illustrate how it works for the if-then-else type of expression. So here we have if, and we have sub-expressions E1, E2, and E3. So the first thing that we're going to do is compute the microfactors for E1, E2, and E3. Now, we look at E1, and we say that that's part of a test. And we're going to make our lives easier, we're going to introduce a temporary variable to express the result of the test. And we're going to call it x. And now we're going to say that this microfactor E1 is actually about the variable x. Okay, now how do we deal with E2? Well, we make the following observation. If x happens to be true, then E2 is a relevant microfactor. So we attach the condition x equals true to E2. But we also have to deal with the case where x is false. So when x is false, we have then E2 is irrelevant. And the way we capture that is by associating x is false with the microfactor 1, which is the multiplicative unit. So it means that it won't have any effect on any multiplications in which it's involved. So finally, we produce this entire microfactor from the then clause. And similarly, with the else clause, we associated E3 with the condition x equals false, and when x equals true, we get the unit microfactor. And we have a similar process for each kind of expression. So now we've produced these.
And the point is you're going to multiply those three values together.
Yes, yes.
And one is multiplicative identity.
Yes,
Right, okay.
yes, right. These microfactors, we're going to have a sum of products expression of these. Right? So we're going to have, in our case, over here, we're going to have the sum over x, because that's a temporary variable that we produced, of these microfactors represents the answer to this expression. So the final step to get from the microfactor to the solution, as I mentioned, it's the variable elimination algorithm. But I just want to add that it's a structured form of the variable elimination algorithm that was developed for object-oriented Bayes nets that allows you to exploit also the independent structure that holds between objects. Okay, just a couple of notes on the inference algorithm. I haven't talked about learning. Learning is basically a pretty standard version of the EM, expectation maximization algorithm. In the EM algorithm, the hard part is always how to do the expectation step. That's the probabilistic inference that I've been talking to you about. Decision making uses a backward induction algorithm, which is like influence diagrams. It turns out there's a nice interplay with the memoization that as a result of the fact that IBAL uses memoization, you automatically get the value iteration algorithm of Markov decision processes out with no extra work. It comes out for free. So just to conclude, so one of the things that I learned is that stochastic programming languages are much more complex than they appear. The first paper that I wrote with David McAllister and Daphne Kohler on this topic came out in 1997. And we wrote basically a stochastic Lisp type of language. And we wrote down an algorithm, and we really thought that it worked. But it turned out to be much, much harder, and it's taken 6 years to really get things right. I learned that it's not productive to try to find the single inference mechanism that works and does everything that you need to do. It was a major breakthrough for me when I realized that I needed the two different phases of inference, and that really simplified things. An interesting thing is that a number of different approaches to first-order probabilistic reasoning ended up having a contribution to make to the solution. So there is the track that's based on knowledge-based model construction. There is the object-oriented type of track. There's the probabilistic logic programming track. There's the functional programming track. And it turns out that all of them had ideas that contributed to the solution. And lastly, one of the major stumbling blocks in the implementation was this issue of laziness and memoization not working together. And it's very easy when you're designing the system to state some goals. And they all seem to be simple goals, and you think you know how to achieve them, and it seems laziness, yeah, we know how to do that. Memorization, yeah, we know how to do that. But sometimes it's the interactions between the goals that can really get it. So to conclude, IBAL is a very general language for constructing probabilistic models. As I hope to have shown you, it can express many existing frameworks. It can capture interesting new ones as well. The core idea is that an IBAL model looks like a program. So building an IBAL model basically amounts to writing a program in a probabilistic programming language. And the key message that I want you to get is that there is a core resemblance between probabilistic reasoning and programming. And just a couple of words on future work. The inference algorithm that I've talked about is an exact inference algorithm. It computes the exact probabilities based on the specification of the model. In most cases, that's going to turn out to be feasible when you get interesting models. So clearly, approximate inference algorithms are needed, and there are a number of candidates to try, and that's definitely a next step. There are also things to do to improve the ease of use of the implementation, to make it easier to work with data. At the moment, all data has to be inserted as observations in the program. There is no notion of reading a file of data. That would be a nice thing to have. And also an interface for basically an API that you could just interface to IBAL rather than have to. At the moment, the only method really is to generate IBAL code and run it. And that's it. Here's a URL where you can obtain IBAL.
Well, thanks, Rory. It's really
Yes.
When you compare it with like a message passing algorithm, say for in a Bayesian network, meaning in a message passing algorithm there is a schedule which is involved. You compute this first, and that automatically gives you a structure on which you run the program. In this case, are you actually trying to find that automatically through a program? Because generally, if the graph is given to you, you already know a scheduling or a procedure of how you want to run the inference on the graph.
Okay, so message passing algorithms. The Perl's polytree algorithm is only for singly connected networks. It doesn't work on loopy networks. Then you get loopy belief propagation, which is an extremely popular algorithm, but it's an approximate inference algorithm. So in terms of exact message propagation algorithms, okay, so there is the junction tree. The junction tree algorithm is essentially a message passing algorithm where you merge nodes in the network together so that it becomes singly connected. That's one way to think of it. There's a very close relationship between variable elimination, which is the algorithm that I end up using, and the junction tree algorithm. You can view the junction tree algorithm as essentially being a compiled form of variable elimination, where if you know what order you want to eliminate the variables, you can set up the junction tree in such a way that the message passing will accomplish exactly the same thing. So one could also, in IBAL, when it comes to start multiplying these microfactors together, one could just as well set up a junction tree and do it in a message passing framework.
Can you detect loops directly when, suppose I give you a pathological case and I run, can the compiler automatically find out that there's a loop in the graph? Or?
Well, yes, because I mean, it does the graph analysis. The point of building the microfactors is actually to be able to do that, because you're no longer working with a program. You're working with a set of basically potentials, and the graph, the BaseNet graph, or the Markov network graph, or the graph of any graphical model, is actually built up out of these potentials. It basically has an edge between any two nodes if they appear in the same factor. So once you have the microfactors, you can construct the graph. You can do whatever analysis you want. You can triangulate the graph. You can build the junction tree.
But the hardest part is to determine the factors itself. I mean, knowing which one are the conditionally independent factors, in meaning the independent clicks which contribute to the final solution. I mean, once you find out, then the marginalization, you can just eliminate variables just by a particular schedule. It's only that you have to find out the individual parts of the graph which don't interact in a complex manner.
I'm sorry, I'm not following.
Well, I can talk to you later.
Okay.
question. Let's thank the speaker again for wondering.